My name is Nitin Verma, and I'll be the moderator for this session. Welcome to the Great Learning Masterclass with Dr. Abhinanda Sarkar. Let's try and keep the session interactive. There is a chat box on the right side. Please ask your questions there, and I'll be routing them to Dr. Sarkar during the session. Our topic for today is business applications of data science, AI, and machine learning. Before we start, I'll quickly introduce Dr. Sarkar to you, for those of you who don't know him. Dr. Sarkar has quite an illustrious career. He's a Ph.D. in statistics from Stanford University. He has over 28 years of teaching experience at prestigious institutions like MIT, Indian Institute of Science, IIM Bangalore, amongst others. He also has a lot of industry experience at companies like GE and IBM. And now, of course, he's the academic director for data science and machine learning programs at Great Learning. So without further ado, I'll hand over to Dr. Sarkar. Sir, please start the session.
Okay, so what I'm going to do is I'm going to share my screen.
We can see your screen, sir.
Okay. Good afternoon, good morning, good evening, based on your time zone. I hope you're all keeping well and safe. These are interesting times. And we will be referring to a variety of topics today, primarily built around three ideas: the idea of business, the idea of data, and the idea of algorithms and technology and things of that sort. I have only my screen in front of me, so if you have questions, please post them. Nitin will keep me connected. And also refer to a few buzzwords, words that are current, and I'll want to explain a little bit about what the particular jargon means. Some of this I do understand, maybe things that you are familiar with or comfortable with, but still the point is to put a story together, see how the different pieces fit and what it means for each of us. This is a busy slide. It's got 3 rings in it, and I'm going to keep it in front of you for about a minute so that you can focus on the parts that makes most sense to you. So this picture is a picture that you'll see various versions of. It is not mine, although the story that I tell today obviously has aspects from my experience in industry and academia. But this view of the world is a view shared by many folks in academia, in industry, in consulting, and government. And it is based on an intersection of 3 things. What are the 3 things? The first ring on the top is business. Business in the usual sense of the word business. A for-profit company, an organization whose purpose is to make a product or a service and to sell it. In doing so, it incurs a cost and makes that up with revenues and then reports a profit. Business operations are, of course, backed up by strategy considerations, which essentially are about trying to understand where the business is going and how can I make good decisions based on that. Business is primarily a human activity. It doesn't really have anything to do with data. It has to do with making goods and services and making it and selling it and running an operation. It could be a big corporation, like a G or an IBM. It could be a small shop in your neighborhood. It has to do certain things. For example, it has to sell. For those of you who have seen things in accounting, the first line of things like balance sheets is often revenues. And you have to begin with sales and work it back into a variety of things that businesses do. The second aspect of this is technology. In this case, information technology, which refers to the use of computers. Computers not just alone, computers in networks, working together with each other through things like the web or the internet, through a variety of devices, for example, mobile devices. And these computers are taught to do certain things. They are coded, they are programmed. So information technologists are professionals who are involved in making and building computers, putting them in networks, coding them up, and building applications on them. The third ring, what I've called models and methods, is about ways in which we can understand the world through mathematics and its various symbols. For example, we can think in terms of modeling the world as what mathematicians call functions, or modeling the world through what statisticians call distributions. This is a language. It's a way to say, this is how I can express a certain situation going on around me in terms of symbols. When I put these three together, I get interesting combinations. When I put business and strategy together with a mathematical language, I get business analytics. And I can solve wonderful things with business analytics. For example, I can ask questions like saying, how should I price something? Let's say that I want to increase sales. And I say that, okay, let's bring prices down. If prices come down, sales will go up. How does sales react to prices? Maybe I can describe that using things, for example, that economists call elasticities, elasticity of demand. Or I can say that what happens if my price comes down by, say, 10%? By how much do I expect my sales to go up? Can I predict sales? What is called predictive analytics. I can also say, let me say that I have a sales target. CEOs of organizations will set targets to companies saying that this is what we must be able to sell. What would be a price point that will help me get there? A prescription, so to speak. And I can optimize various things in order to be able to do that. Do I want more people buying my product? Do I want the most revenue? Things of that sort. So this descriptive, predictive, prescriptive view of the world is primarily what business analytics concerns itself with. On the other side of the story, I can ask the question that if I am running a business, then how does the world of technology support me? Today, you see many companies that are using the term digital to express this thought. Digital, as opposed to analog, could mean all kinds of computing and all kinds of technology. But in this particular case, what it means is a specific set of information technologies that help a business do its job better. Specific examples of it could be the use of mobiles in order to be able to get products and services to consumers. For example, social media, which allows a company to reach out to its customers for marketing purposes and also for feedback, or the service itself could be through social media. I'd also like to mention the notion of a cloud. Now, cloud for computers is effectively a computer that is sitting somewhere away from the location of the application. And the purpose of the cloud is to be able to hold data and to hold programs, and for that data to be made available to people and that program to be run by other people so that a product or a service can be generated. The cloud itself is a product or a service and is making a major difference to what the world of technology brings to the world of business. Away from the world of business, you can think of using computers to enable models that derive their power from data. And this is the scope of machine learning. A machine here refers to a computer, and the computer is learning. Learning from what? Learning from information, what we refer to as data. And this data comes in a variety of forms. And that data is modeled, as I expressed, through functions, distributions, and various ways. And they are programs that are built on top of that data in order to teach the machine something. Now, what can we teach the machine to do? In general, we can teach the machine to learn specific rules. For example, we can teach a machine to say that if a person's face is looking very serious, maybe he's a little angry, he's smiling, I'm not doing a good job, am I? Maybe he's happy. So we can teach a machine a variety of things based on certain rules that it can learn from data. What do most happy people look like? What do most sad people look like? Is that information on the image that gets me that information, and therefore I can model it through an equation, and I can program that equation, and I can keep improving that equation as more and more data comes in. The machine learns from a mathematical model that has been programmed into it, building on data. Which brings me to the middle and the idea of data science. Data science is a relatively new field. And what it does is it tries to combine the idea of a model that is implemented on a computer and is used for a specific purpose. For our purposes in this talk, this is a business application. But it could be any use. It could be finding planets up in other solar systems, gravitational waves. It could be finding genetic structures of bacteria or viruses. The application domain for data science could be wide and varied. And what we are focused today is the business application of data science. So for me today, what is data science? It is the use of mathematical and statistical models for solving a business problem or taking advantage of a business opportunity deployed through a information technology setup, a computer or a network. Now that's a mouthful. And we'll see what that means in specific contexts as we keep going. One thing I'd like to say before I kind of move on from this slide is that there is a tendency sometimes to believe that something in the middle of a picture like this, say data science, is a holy grail, something aspirational for companies, for individuals, for technologists, that we should aspire to be data scientists and companies should aspire to do data science. This is correct. However, it's useful to remember that the middle of this picture emphasizes breadth. The usefulness of business with the capability of information technology and the power of mathematics. That's breadth. But as you move away to the top, to the left, and to the right, you get depth. And depth is certainly important. It's important to have the skill to know what will sell in a specific marketplace, to have a business gut. It's important to have an understanding of how computers can be taught to do certain things, programming, be that your particular skill, maybe Java, maybe Python, maybe C++, whatever be your language. And it's important to have deep knowledge of mathematical and statistical models. So it is important to have individual depth in these things as well. And the community of data science relies on this depth. So if your individual expertise is in sales, or your individual expertise is in programming, or your individual expertise is in statistical analysis, so be it. That depth is going to be very vital to the organizations that you support in order to build the story together. Some organizations are built on breadth, some are built on depth. Individual careers are often built on breadth, individual careers are built on depth. Choose your approach, choose how you might proceed in this journey for your organizations and for yourself. The reason I say that is, once again, to emphasize, I do not want to leave you with the impression that this is entirely about what goes on with business, IT, and models all put together. Separately, these drive the world in their own ways. Let's take a look at a specific example of how this might shape up. This is an example of a digital hospital. This particular breakdown of it comes from an IBM white paper, but many organizations have implemented various aspects of something of this sort. And as you can see, the business of a hospital, so to speak, and once again, I emphasize that I'm thinking today of organizations as businesses. A hospital as also a business entity. So therefore, what I need to do is to be able to identify what are the specific digital opportunities where a model or data can play significant roles. As an example, from the pure business perspective of doing this, one can think, for example, of financial management of a hospital, which includes, as I said, ideas of pricing of services and of managing costs around it. One can think of things like telehealth, which involves transmitting data over a network, connecting a patient with a doctor, and transmitting data, for example, of the form of scans, of medical reports, etc. You can think in terms of medical grade networks. Let's say you're setting up a cloud service. What kind of service might that be, and who might need access to it for various purposes? You can think of what data would be needed. Data, for example, of patients coming in, patients leaving, what are the services that they availed. You may also need to track them, figuring out what patients are going where, when do they need specific follow-ups, and therefore build models of saying, this is the kind of patient that would be needing a lot of follow-up. That kind of model may involve understanding the progression of a disease. A cancer patient may require to come to a hospital for treatment over specific durations, as may, for example, a diabetic or someone who has been in an accident and a bone needs setting. Within a hospital itself, management of resources, for example, bed management. Who are the patients that I have now? How long do I expect them to stay? When might a bed become vacant? Can I do planning around that? What might be the data that I would need in order to solve that problem? For example, how much time is associated with specific disease conditions? A heart patient after surgery would require a bed for how long typically? This is not a mathematics result. Some patients will recover quickly. Some patients will take a long time to recover. So I cannot write a rule, but what I can do is track a patient and see what category of patient this is. And I can group patients and say that this patient is following this prognosis. This grouping of patients or grouping of data points is something that people in machine learning sometimes call unsupervised learning, just the grouping of patients without any specific outcome in mind. So different kinds of algorithms and different kinds of models are used by data scientists and machine learning professionals, by business analysts looking to predict costs and prices, and by IT specialists looking to see what service can I put where and how do I connect people effectively. Now, all this, of course, becomes much more important in specific circumstances. Let's say a circumstance here. I hope you can read this. So what I'm talking about here is the tracking of an epidemic, obviously a topic of relevance at this point in time. And the idea that says that how are we going to put three rings that I talked about to solve a problem of this kind? How do I set up a network to communicate with patients who can no longer visit me? How much data do I need in order to do that? What kind of service provisioning do I need for my service provider? Once I have been able to track my patients, how do I identify the hotspots? Where is the disease growing much faster? What kind of analysis do I need to do in order to be able to do that? How do I connect patients with specific geographies? For example, things like geographic information systems. A hotspot may be something in space, a location. It may also be in time. It may be moving, a moving target, which is what epidemiologists fear the most. Then we need to take certain decisions. For example, on medicines that we might need. Which medicines do we need and where and how? What purpose will those medicines serve? So for example, we can come up with various rules by which we can decide, by which we can decide where and to whom the medicines would go. This may sound like playing God, but in the purpose of the hospital, this is still a decision that needs to be taken. And in the context of that decision, how do we manage things like cost and quality, which, like sales and price, may be trading off against each other? We may say that I will be able to give you a better medication, but more time and more cost will be needed in order to get that medicine to the market. Someone in the administrative system will then figure out where that cost is going to come from. That may be outside the scope of what we are doing, but that calculation is very important to be able to do. In order to be able to link specific outcomes like cost and quality that can be measured, the specific features of the medicine and of the patients I'm trying to serve. When there is a specific target of this kind like cost and quality, people in this world refer to this as a supervised learning problem. I'm trying to learn more about the cost and quality implications of what it is that I'm trying to do. These obviously are complicated problems, but that is precisely where things like putting business and models together to understand the spread of diseases helps in building a good analytic story. Understanding the technology infrastructure and the business implications of it, and therefore the right digitization, makes it all possible to deploy on the ground. And the algorithms that come at the end of it, the algorithms running on those computers with specific models that we might build, will be very, very important in order to decide quickly and effectively what it is that we should be able to do. In this particular case, which medicines need to go to which hotspots. This is an example. There are many other examples in many other industries. If you're simply running a shop, for example, as I said, you could think of prices, you can think of inventories. What should I order and when? How do I even lay out or organize my material if I have a shop? How do I write it on a piece of paper and therefore on a computer to see this is the kind of material that I have in stock and this is what I need to order? So whatever be your business, there will be a version of it that looks something like my story of a digital hospital here. And what I'd encourage you to do is to think of the organizations that you work for, work with. If you're a student, you aspire to work with, and see around you and see if you can build a similar digital story. And out of that story, the three pieces, so to speak, will fall out. The business model for the organization, the IT infrastructure for the organization, and the way that can be translated into a model that can run on the IT and solve the business problem. This, as I said, is an example. It is not my entire story today, but I'd like to hear your stories. What is it that's on your mind? What kind of businesses are you working with? Is there something that we can talk about today that's going to make this story a little more complete? Let me stop for a while, bring this back to Nitin, and see if there's something interesting on the chat or something that he can point out that we can take this towards.
Sure, sir.
Sure.
So lots of questions that have come in. And,
yeah. Can you just summarize and I will address as best as I can.
I'll try to pick a few. So there are a couple of people who are asking, how do AI and ML predictions work? Uncertain scenarios like calamities, like what we are facing right now. And the question, Vikayat Goyal and Shekhar Pandey, they're asking, say, for example, while you predict sales, you can never calculate the impact of natural calamities. How do you take informed decisions then?
Okay, so given the context of what we have, this is a very pertinent question. So let me answer this using, let's say, an example from a slightly different world. Let's say the world of weather and climate. So weather is what we see tomorrow. Climate is what we see overall. So weather forecasting, for example, is something that has been going on for quite some time. And typically it initially uses statistical methods. And it is now using much more sophisticated programs on various kinds of physics-based models. Physics comes in here instead of business in that particular application. And so we can do a routine weather prediction. But now the question arises is, can we predict a major storm? Can we predict a calamity? How can we do that? Can we predict a cyclone, for example? So how one does that is one has a mathematical model of what a cyclone looks like. For example, the fluidic motion of air in water. And we put that together and we build a mathematical equation for that. And then we put it into a high performance computer and see how that cyclone evolves and when it will strike. So it's a combination of a very strong mathematical model and an estimation of that model based on data from satellites. Relating that back to the situation that we are in the world today, there are epidemiological models that exist right now. For example, one particular model is called the SIR model, which has certain parameters. These parameters can be estimated from the data based on observations in the field. And then what happens is that this is a set of differential equations. They can be simulated on a computer. And these may require very extensive simulations to say, where is this disease going to go? Which is what the world is doing right now in trying to understand where is this particular calamity that we are facing now headed. So it is not purely data. It is not a statistical regression, shall we say. It is not a pure mathematical model, because a pure mathematical model cannot adjust to conditions of today and in a specific country. And it is not a question of storing enough data on a computer and running simulations. Because if you do not understand the biology and the medicine and the weather associated with this, you'll not be able to get to an answer. So a combination of data-driven simulations based on domain understanding models is what is being tried to get this. Are we getting it right all the time? No. If we were getting it right, we know exactly what the state of each country would be when. But we are not in no man's land. We do have a rough idea of what's going on. By we, I mean generic we, not me clearly.
Okay, thank you, sir. I'll read out another question. This is from Abhishek Srivastava. This is a question related to the example that you just explained. So he's asking, is this hospital example an example of supervised learning or unsupervised learning?
So different aspects of it could be supervised and unsupervised. So there are many things that are here. So for example, CRM, patient and billing. I could set up a problem that says that this is a patient that I am probably going to lose, or this is a patient from whom I'm probably going to have to figure out how to recover payment. If I can track that, and that is a response, the response of the patient, and I can model that using other characteristics, that is an example of a supervised learning method. I'm trying to understand patient behavior based on something else. There could be parts of this that are unsupervised. So for example, I think, let's pick another one, staff scheduling and credentialing. So essentially what this means is that can I take staff as I see now and group them into different buckets based on their tasks, based on their experience, based on where they live, based on their transportation, based on their utilization in the hospital, based on all of these, can I group my staff into various categories? That is an unsupervised learning problem. Supervised learning means there's a specific variable that I need to explain using other variables. Unsupervised means there is no such variable. All of them are being put together in order to understand it together. That's a big topic, and we hope to be able to spend more time on it elsewhere and elsewhere. But across this, there are all kinds of examples of various algorithms throughout.
So I'll just take a couple of last questions before we move on. So there's Praveen Kumar who's asking, from an investment perspective, when is the right time for an organization to invest in data science? Is there a gradation that you can suggest?
So organizations typically need a certain amount of maturity to invest in data science. So if the investment is thought explicitly in terms of data science, it should have an IT infrastructure in place. It should have a certain, shall I say, modeling capability in place, and it should have an understanding of the domain in place. In the absence of this, it may not make much sense to think of the effort as a data science effort. That being said, it doesn't mean that the organization cannot proceed. It can absolutely proceed by having very good analytics that's built on sales and financial models, that's based on a very strong IT backbone of data, and is based on maybe even a good understanding of how, for example, investments might be made and investments might be optimized. So all the pieces might be there. As to whether it's worth an organization's while to structure it together as a data science initiative is a cultural thing. Some organizations prefer doing it that way. In other words, building a data science organization and putting it together. Some do it separately, keeping the things separate, and then at the CXO level, saying strategically, this is how we will solve a specific problem using our business acumen, using technology, or using our understanding of the domain.
Okay. So I'll just take one last question. This is from Bethel Emmanuel. Question is, this is a little broad. So the question is, what is your professional advice to someone contemplating a career between business analytics versus data science or machine learning?
That's up to you. If your heart is in coding, if you're a person who's passionate about making computers do their bidding, approach it through machine learning. If your heart is in making money in buying and selling things, approach it through business analytics. My advice to people tends to be approach it from a place of comfort for yourself, so you get a little confidence in what you're doing, and then learn what you need to do. It doesn't matter. You could be a businessman learning how to code. You could be a programmer learning how to sell. You could be a mathematician trying to figure out how costs can be calculated. Come from your comfort zone, whatever works for you. Okay, thanks very much. Let me move on.
Sure, sir.
To one more point that I wanted to cover today, since we are talking about words and what they mean. We live in a world in which there is a substantial amount of what I would say size, volume, lots of things going on. And two particular aspects of that are what are often referred to as big data and deep learning. I just wanted to address these before moving on to something like AI. Big data you've heard of. Big data simply means lots and lots of data coming from different places. From what humans do, for example, social media, from what machines do, for example, from sensors and what is often called the Internet of Things. And this data comes in major quantities. We are doubling our data once every 10 years, 20 years as we keep progressing. All kinds of variety, things like texts and images and videos and various signals. Velocity coming at us extremely quickly. We can hardly keep up with the amount of data that's coming at us. Just think of just looking at the internet today and being inundated with information. Think of the network bottlenecks that we often face when trying to place a mobile call and maybe calls get dropped, etc. The speed at which information moves. And veracity, which of course essentially means is the data that you're seeing correct, true, reliable? And could also refer to, for example, things like, is the data safe? Is the data secured? Are only the people who are authorized to work on the data working on it? The notion of cybersecurity. Securing the data in a place in which it can do good and ideally no harm. Now, what is all of this being used for? All of this being used in the scope that we're talking about today on computers. And given the kind of volume, variety, and velocity that's coming in, you need specialized machines to be able to do this. For example, you might need graphical processing units, which are specific computer chips whose purpose was to deal with graphics, images. But because images deal with data, a lot of pixels coming at you suddenly all over the place simultaneously, there are also chips that can do multitasking very, very well. Not at the chip level, but at the computer level, you can put many computers together, many processors together to build supercomputers, which often need to be put in very specialized places where heat needs to be dissipated, etc., etc. And all this data, through various things like natural language understanding and computer vision, etc., is contributing to the notion of deep learning. Deep in the sense of we're going deep into human understanding, not just in terms of numbers, which is what computers are very good at doing. Computers are essentially sophisticated versions of zeros and ones. So therefore, how can I convert language and vision, natural language and vision, into zeros and ones? And recent innovations in deep learning and things like called deep neural networks have made this a very attractive area of research, and have also subtly made this kind of data fit into the world that I was talking about, fit into the world of machine learning, business analytics, and digital. And what deep learning has done, this kind of ability to deal with words and pictures has done, is it has put a layer on top of those three rings that I talked about, and we call that artificial intelligence. Artificial intelligence historically has meant many different things. It has meant historically, for example, the idea of creating an intelligence based on a machine, a robot, if you want to think of it that way. Learning the rules of the game as it goes along. And that kind of artificial intelligence still exists. For example, through a method that's sometimes called reinforcement learning. Reinforcement learning means teaching a robot, let's say something that's playing a game, say chess, and saying it, these are the rules of the game, now play it. And when you have played well, I will give you a reward. When you have played badly, I will penalize you. I will reinforce your learning. And in doing so, teach you. As autonomous vehicle, let it loose on the road, on a test road, not on a real road, mind you, and see whether it can do the right thing. Can it stop? Can it take a turn? And when it does it correctly, figure out a way to reward the algorithm, saying, do more of this. And when it does it incorrectly, and something gets hit or hurt, penalize it. But today, AI means something a little different. It means, give me all the data that you have, and I will learn new rules. New rules from images, new rules from text. New ways of understanding sentiment. I am saying something. I said that this movie is good. That means that I like the movie. It's a positive sentiment. The customer says that this product sucks. Apologies for the language. But the computer will say the word sucks in this context means that this is not a good product. Can I build those rules not by me programming the rules into the computer, but by the computer itself knowing that these words mean positive things and these words mean negative things? That kind of sentiment analysis is beginning to revolutionize how computers can understand what we say. Not because we have told them, but because we have given them enough words that they can figure it out. We also need to tell them what is good and bad, what is positive or not. A question got asked. This is another example of supervised learning. We need to supervise the training of this machine. What is the variable that is doing the supervision? The known sentiment of the text. Similarly for images. What does this particular image mean? I look at a grocery store and I look at the shelf, and from it I can identify this product has been sold and this product has been sold and this product remains and this product remains. And I do that simply by looking at an image of the shelf, not by tracking it through a QR code or anything like that. I can look at medical images and look for cancer lesions, etc. So long as the computer knows what it is looking for, it can mine the data, discover the exact nature of the rule itself. The mathematics behind this gets complicated, very complicated, so complicated that nobody understands it. There's major research programs going on to understand why deep learning works. But why? How does it work? That's easier to know. Because the computer simply optimizes its rules so that it gives the right answer most of the time. Give it enough data and the mathematics becomes less relevant. Now, how does this all play, for example, into specific kinds of applications? So an application in this particular phase, and I use the word application in the way that an IT professional would use the word application, which is a piece of code that executes a task. So an application, what it would need to do is it would need to have the skill and the capability of processing this amount of data. Now it can do that by either being very clever about the data that it takes. For example, it can say that I will only look at certain words in the text. I will not look at all the words. There are words like a, and the, which are not telling me much. Let me remove those. In other words, be very, very clever about saying that the relevant part of big data is much smaller than the total amount of data that is there. Let me find the right words from this huge body of text. Let me convert big data into information, big information, but not play around with the entirety, but playing around with the useful part. So that's one kind of thing that the application does. The second kind of thing that the application does is that it takes the data and it runs these algorithms over and over again, repeatedly, many times. The point of learning is that it has to happen continuously. And so a computer has to be programmed well in order that it can repeatedly do this. Computers are naturally good at this. Computers can naturally store a lot of information, and computers can naturally do a lot of calculations quickly. That's essentially what computers are. They're storage devices and they're calculators. And in the world of big data and deep learning, these two pieces are coming together very effectively. Large amounts of information stored is being computed upon very, very quickly. And so therefore, what this is meaning is that new ways of coding, new ways of programming, new ways of enabling a software to do this are developing. Things like software as a service is coming into being and being used here so that a large number of people can do this kind of thing without necessarily being deep experts at the algorithms. Because if it was, then artificial intelligence would be the domain of very few people. But the programming world is also reshaping itself in order to be able to do this. What does this mean for businesses? What this means for businesses is two things. One, find a service that can store your data. Number two, find a service or an application that can run your code. And we're slowly becoming, I wouldn't say slowly, I'd say quite rapidly, this is becoming easier and easier to do. And so therefore, artificial intelligence has become something that a business can now routinely do, either by deploying a chatbot or by image-based search engines, or by a variety of rules that it might deploy in order to, for example, to say, will the customer default on my loan? Will this particular patient, will this particular, say, network, my cell phone provider, lose this particular service that I'm looking for? So therefore, these rules can be built out of it without the necessary expertise that was necessary 10 years ago. This combination of data storage and democratic or easily executable code is leading to very big changes in business. Let me give a little example. This is from the aviation industry and what I would call the aviation Internet of Things. And as you can see, there are planes taking on and off. This is an airport. This is a control tower where there are people watching what that aircraft is doing. There's a device that's tracking the planes itself. The planes are coming in, passengers are getting on and off. The planes are then going, being inspected, made sure that they're safe. And this process repeatedly keeps going. A very data intensive process. Lots and lots of things are going on. As you can imagine, this requires enormous precision to make sure that the planes are taking off on time, that they're using runway spaces well, that airspace is being used well, and air traffic controllers manage it. Computers manage a lot of it. How much time will the plane be off for maintenance? What parts do I need? All that will need to be put into a range of business applications. Now, artificial intelligence can help in this, of course. It can have various, shall we say, additional layers above and beyond what, let's say, the aviation industry is doing at this point in time. For example, you can try and get information on the signals from aircrafts. Lots and lots of sensors tracking various things like position, altitude, that's X, Y, and Z coordinates, status of fuel, status of vibrations, electrical condition of the plane, etc. All that can be tracked. There can be heavy computers on the ground. What is the information that I need to be able to transmit? How should that be compressed? How should that be stored? How should that be analyzed, real time or backed up? That's an intelligent decision to be made. The voice recorders, the air traffic controllers are tracking all of this. Can we look at what they're saying and get a better idea of what is going on in the airport? What are the places where, shall we say, there's congestion, more that's going on? Can we make their lives a little easier and therefore make all our lives a little safer? For the inspection of inspected parts, images of inspected parts, can I look at parts and use imaging algorithms, clever imaging algorithms? For example, I can look at something, let's say this is a part here, and I can scan it on top. But maybe there's a crack that's developing underneath it. Maybe there's something inside. Can I get an imaging device that goes in, say an ultrasound, that goes into this, and as it penetrates the material, if there is a crack, it vibrates this way. Can I do something of that sort and put that information together and therefore do preemptive, shall we say, I won't say guesswork, but preemptive, predictive maintenance. I'm certainly not guessing whether the parts are going back or not. I'm doing a lot better than guessing, but I'm doing it without being able to see the crack. So therefore, as you can imagine, that the ability to deal with these new kinds of unstructured information is leading to lots and lots of new opportunities for, let's say, the aviation industry and for many other industries as well. Imagine, if you will, the banking industry. The banking industry is now focusing on having fewer branches all over the world. We're mostly doing our transactions via phone calls, or we're doing it on the internet by typing things up. Telebanking. At most, we may go to an ATM machine. How is all that enabled? Is it done through things like chatbots that respond to our queries without having lots of humans necessarily having to pick up all the calls? Is it done by secure transmission mechanisms so that we can move money from A to B, from bank A to bank B, or to pay someone online safely and not worry about someone else getting into that account and moving the money around? Is the necessary cybersecurity in place for being able to do that? Can I learn about fraud? Can I understand how new patterns of misbehavior are being thought of? New ways of skimming money off? New ways, for example, of, shall we say, removing money from ATMs? And remember that a simple supervised learning algorithm here may not work because the person who's doing the unethical behavior is also changing their behavior. And can a machine learn that behavior quickly enough so that it can stop it before it happens again, and before the unethical entity tries a different approach? This needs to go well beyond traditional statistical modeling because the rules change. And are we intelligent enough to learn these changing rules in time and stop fraud and such matters? So the financial services industry certainly is concerned about this world and is taking heavy advantage of it, just like aviation and any other industry. Once again, think of your industries, think of where you are, and think of where this kind of big data, deep learning, and AI can help take the next step, either for your organizations, perhaps for yourselves. Let me stop now and again go back to Nitin and see if there are interesting points that you might have regarding this.
Yes, sir. There are lots of questions that come in again. Very interesting questions. I don't think we'll be able to take all of them. I'll just pick out a few to answer. So there are a couple of questions around what is the importance of psychology or cognitive science in modeling human behavior and how it can be implemented to understand human decision making or make sentiment analysis. And then people are asking, can AI replace humans? Like, these sort of questions. This is from Vishal, Ahuja, and Satish.
Okay, so on the sentiment side, to go back, intelligence is based on, of course, neurons in our normal brain. And when we talk about neurons here, effectively electrons moving around in my head. If the electron moves a small distance, we call it chemistry. If it's a big distance, electricity. But it's basically electrons moving around here. And the rules that come out of this kind of movement of electrons in my head is what we refer to as psychology. So now the question becomes that, is an understanding of this kind of rules of psychology, shall we say, playing a role in artificial intelligence? The answer for the current generation of artificial intelligence is no. The reason is that what is happening right now is that deep learning, by looking at things like pictures and words, and by learning directly from them, is short-circuiting the psychological process. It's short-circuiting the cognitive process. In other words, a computer is developing a cognitive sense based on machine learning, which is unique to it and has nothing really to do with human psychology. But your point is well taken. Can we put these two things together? There are organizations, for example, MIT's Media Lab, etc., that are building bridges between these two ways of thinking. A kind of empirical data-driven machine learning way of thinking that with deep neural networks is doing a very good job, and a psychological way of doing things that we don't fully understand because we don't understand neuronal collections and my hippocampus and my cerebellum, etc., etc. So in short, artificial intelligence has moved away from understanding psychology into something that's a lot more empirical and pure data-driven. But the hope is that deep learning will lead to a new theory of intelligence, a new theory of understanding that this is the way psychology actually works. Is our brain a convolutional neural network or a recurrent neural network in a more advanced setting? Time will tell. But there are people who certainly think that. But right now, AI is an empirical science. And I think we as a businesses are taking full advantage of that. We know intelligence without understanding psychology.
Okay. I hope the question has been answered. So the next question is from Garvit Nagpal. He's asking, how do we ensure credibility of data and what are the factors to be considered while collecting data before we get
Yes. So obviously you garbage in, garbage out. So obviously if you are not getting good data, you're not going to get reliable answers. Or let me put it this way, your answer only applies to the data that you get. If you're, for example, training an autonomous vehicle that is only being trained on a certain kind of road and only seeing certain kinds of obstacles, then you give it a new kind of road and a new kind of obstacle, it will not be able to perform its task adequately. So the way to do this would be to be able to say that, can I take the data or can I take the problem and then understand what is the right data in order to be able to model my situation correctly. Do we do this well all the time? No. Certainly the world is using a certain kind of data that's more easily available. And it is importing it to other parts of the world where it may not be that correctly applicable. And this may be true not just for, let's say, search engines, but maybe also true for epidemics, maybe true for medicines that may work in different parts of the world. Design of data is something that comes from other fields. For example, last year, the Nobel Prize in Economics was given for cleverly designed randomized controlled trials. How do I take the data correctly in order to draw the right inference? Maybe we need to do something of that sort and the time is coming. But right now, we need to design our data in such a way so that it fairly reflects the use case of the algorithm that I have. Limited data, limited use. I want broad use, my data must be broad. There's really no bypassing that approach.
Perfect. Okay, we'll take a couple of more questions. So there's this question from Nihal. He's asking, what about data science and e-commerce? How can we leverage analytics in e-commerce and how far have industries gone so far? Your views in that?
So e-commerce has a number of aspects to this. One aspect to it, of course, is the network aspect, the E part of it. In other words, enabling the backbone, making sure that the backbone is strong, making sure, for example, that you can do, say, money transfers, payments can be made, etc., going to the extent of things like digital currency, which was in vogue till some years ago, still is. So there's a backbone part of e-commerce, which is to make sure that the analytics is in place in order to make sure that e-commerce can successfully be executed. Do we have enough frequencies? Do we have enough bandwidth available? Do we have secure channels for payments and communications? That's a network and IT problem. The next layer that sits on top of it, shall we say, is the service layer. In other words, can I put the buyer and the seller together? Can I design auctions in order to be able to do that? Today, most e-commerce sites operate on auctions. An auction is essentially the determination of a price. So can that be done? And so if you go to many e-commerce facilities, that is sometimes visible. There is an arranged auction, so for example, in eBay, or it can be something that's automatic. For example, like a Google ad, where you may not even see the auction taking place. In other words, this mechanics of putting buyers and sellers together requires a kind of analytics such as auctions. And then there's a surface layer on top of it, which says that, can I build intelligence on top of this? Can I find ways in which I can discover if X orders this product, then X will order some other product? Recommendation engines of various things that aren't necessary for e-commerce, but help it grow. So things like recommendation engines, things like automatic ordering processes at the back end that says that this inventory is going down, let me place more orders for it. So both on the customer and supplier side, there are services like that that are put in place. So all layers of e-commerce, from the basic network support layer to the communication layer between buyers and sellers to the value-added services like recommendation engines, are in full flow. E-commerce may not be, shall we say, the buzzword of the era, but it has stabilized into something which has a lot of analytics embedded.
Awesome. There's this one more question which has been asked by a lot of people, and this is quite relevant to us actually.
Sure.
How can data science be used in the education sector to personalize the experience for people?
Okay, I think there are people in the audience who know that more than I do. But let me give a quick question that was once put to me and throw it back to you. I know this is unfair. You asked a question, you deserve an answer. I'm going to give you another question back, my revenge. But so someone is watching a video and you see a point in which this video is stopped and a certain portion of the video is played again. So what you see is that there's a certain portion of the video that is repeatedly being played by the learner, the person who's watching it. So it's going from in your direction from beginning to end, but certain parts are being replayed over and over again. Now, given this, what conclusion might be drawn? Conclusion one, this is interesting and I'm learning something from it. I want to hear it again. Conclusion two, this is difficult. I didn't understand this. Let me go back and let me do this again and see if I can understand this. So now these kinds of questions emerge in education, and if you're trying to use this kind of sort of detailed tracking of content. And so it's not just a question of, shall we say, looking at the data. The educational aspect of this, shall we say, the domain aspect of it is to say that why is something happening? And what is the human behavior that this is corresponding to is, I think, very, very vital in being able to do this. Of course, the basics of it, like in any other business, for example, things like lead generation, what kind of learner would be interested in the next topic, would be applicable to other businesses as well, to be able to have scores and leads. A traditional application of data science is in scoring, for example, using a method called logistic regression to say that these are the high prospects, medium prospects, low prospects. So you can do that as well to track learners. But so from, shall we say, the mundane lead tracking methods to doing video analytics, there's a lot that can be tried out. But like in all aspects of data sciences, let's be cognizant of the importance of the domain in understanding the human element of it, so that we make sure that we're asking the right question and that we're interpreting the answer correctly as to whether this is an easy part of the video or whether this is the hard part of the video. And both may look the same.
Interesting. I think we'll have to catch up more after the session on this.
Okay. All right. The time says I'm done now. Should we let people go, Nitin?
Yeah, I think there are lots of questions, but we'll have to do another session to answer all of them.
Okay.
Stop the session now. Thank you everyone for attending again and making this very, very interactive. For those of you who could not attend the entire session, like we said, the recording will be available on the YouTube channel permanently. We'll be doing a lot more of these sessions going forward. And for updates on these sessions and other content, you should check out Great Learning Academy. I've given a link in the description below. On Great Learning Academy, we have curated 300+ hours of free learning content across various domains like data science, AI, cloud computing. And the content is also supplemented with industry case studies, quizzes, and projects. So it ensures a holistic learning experience. And we'll be posting more about the upcoming sessions on Great Learning Academy, as well as on our social media channels on YouTube, on LinkedIn, and Facebook. I've given all those links in the description below. So for those of you who want to stay updated, please follow us on these channels, and we'll be releasing the next session very soon. Thank you, Dr. Sarkar.
Sure. Bye for now. Stay safe, everyone. Stay safe.
Yeah, stay safe, stay home. I'll be wrapping up the session now. Thank you all for attending again. Bye-bye.